Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
I'm Drew, and this episode is about one of the biggest engineering hurdles humanity has ever faced: how to safely store nuclear waste for 100,000 years. Each time a nuclear power plant runs, it leaves behind something incredibly powerful and incredibly dangerous. Spent nuclear fuel rods stay radioactive for longer than civilization has existed. You can't burn it, neutralize it, or just leave it somewhere. It has to be sealed, contained, and kept stable across a long time. That's a problem no other form of energy has ever created. Right now, most countries only have temporary storage systems. Huge pools of water or reinforced casks sitting above ground, meant to last decades, not millennia. But now, scientists and engineers are building something entirely different: underground repositories designed to outlast everything humans have ever built. In Finland, a project called Onkalo is taking shape. A network of tunnels dug deep into ancient bedrock, with copper canisters and clay barriers protecting waste from corrosion, water, and the challenges of time. In this episode, we'll talk about how these systems work and the engineering to make them possible. We'll talk about how scientists model the next 100,000 years, what materials can survive that long, and why communicating danger to the people of the future is a science problem of its own. But when you're building something that has to last forever, every decision counts. To understand why storing nuclear waste is so difficult, you have to start with what it actually is. Inside a reactor, uranium atoms split apart in a process called fission, releasing massive amounts of energy. That's what powers the plant. The fission also creates fragments of atoms called fission products, and many of them are unstable. They give off radiation as they decay into more stable forms. That radiation comes in three big types: alpha, beta, and gamma. Alpha radiation particles can be stopped by a sheet of paper. Beta particles by a layer of plastic or metal. But gamma radiation cuts straight through almost anything. That's why the waste needs layers of shielding and isolation, even decades after it's removed from a reactor. The waste also gives off heat, because radioactive decay releases energy over time. Even after it's cooled in a reactor pool for years, spent fuel can stay hot enough to melt metal if it's not managed carefully. That's part of what makes deep storage so tricky. Engineers have to design containers and tunnels that can handle both the heat and the radiation for thousands of years without cracking, corroding, or leaking. And the timescale is mind-bending. Some isotopes inside spent fuel cells have half-lives of only a few years, while others, like plutonium-239, stay radioactive for more than 24,000 years. For safe storage, scientists need to think far beyond that. Since you want the radiation levels to drop to something close to natural background levels, that can take 10 half-lives or more, which means designing a system that can last hundreds of thousands of years. It's about predicting how rock, metal, and water will interact over geological time, and making sure that if the surface of the Earth shifts or glaciers return, that the waste will still be sealed off from the surface. That's where deep repository projects come in. If storing nuclear waste were just about locking it in a vault, this problem would have been solved decades ago. The real challenge is time. Steel corrodes, concrete cracks, and water seeps into everything. Over thousands of years, even small chemical reactions can turn into catastrophic leaks. That's why engineers have moved past single-layer storage and toward multiple barrier systems. Structures built on redundancy, where every layer has a unique purpose. The first layer of Onkalo, one of the leading storage projects, is the copper canister. Each one is built to hold about 2 tons of spent fuel, sealed in a thick copper shell designed to resist corrosion underground. Copper doesn't rust the way iron does, and with the lack of oxygen in deep rock environments, it corrodes at an incredibly slow rate, less than a few micrometers per century. Tests in Finland and Sweden show that even after 100,000 years, the copper could stay intact if groundwater chemistry stays stable. Around that copper canister is the bentonite clay buffer. Bentonite is a natural volcanic clay that swells when it gets wet, sealing any gaps and locking out water flow. It acts like a natural sponge and chemical filter at the same time. If any radioactive atoms escape the canister, the clay binds to them and slows their movement to zero. It also provides mechanical conditioning, protecting the copper from rock shifts or temperature changes. The final layer is the bedrock itself. Onkalo is a cave carved into granite that's been geologically stable for over 1 billion years. The rock acts as a physical wall, blocking groundwater movement and isolating the waste deep below the surface biosphere. Even if everything above ground changes, climate, sea level, or human civilization, the bedrock remains constant. To make sure the system actually works, scientists use computer simulations and accelerated testing. They model how heat from the waste moves through the rock, how groundwater chemistry evolves, and how materials degrade under radiation. Some labs even expose copper and bentonite samples to gamma rays and elevated temperatures to mimic centuries of decay in just a few months. These layers don't rely on maintenance or machines. They rely on physics and chemistry staying consistent, something far more reliable than human oversight. Before anything else can be built, scientists have to answer one question. Where can we bury something and trust that it will stay untouched for 10,000 years? It's not a matter of luck. It's a geological search for the most stable ground on the planet. Finland, Sweden, and Norway all sit on some of the oldest rock formations on the planet. Much of their bedrock is Precambrian granite, a type of rock that hasn't moved significantly in over 1 billion years. It's dense, dry, and predictable. That's exactly what makes it ideal for nuclear storage. Granite doesn't erode quickly, and it has very low permeability, meaning water struggles to move through it. Since water is the main thing that could carry radioactive material back to the surface, that property alone makes it a near-perfect natural barrier. But even ancient rock isn't flawless. Engineers need to find sections with minimal fractures and no nearby fault lines. They spend years drilling boreholes, narrow, deep cores that reveal the rock structure, layer by layer. These samples tell them where the cracks are, how much groundwater is present, and what minerals the water interacts with. They then map everything with seismic imaging, sending vibrations through the ground and measuring how they reflect. This lets scientists visualize underground features, the same way doctors use ultrasound machines to see inside the human body. Once they find a stable region, they begin to study groundwater flow. Even the slowest movement of water matters when you're thinking in millennia. Teams inject tracers, harmless chemical markers, into boreholes and track how long they take to appear elsewhere. The slower the travel time, the safer the site. In Finland, for example, groundwater in the chosen area can take tens of thousands of years to move a few kilometers, meaning any potential leak would remain trapped far below the surface. Then there's the question of future geology. Scientists have to think about ice ages, erosion, and sea level shifts. During an ice age, the weight of glaciers can press down on the land, altering groundwater pressure. So researchers model these future scenarios using climate simulations and geological data from past glaciations. The goal is to ensure that even under those extreme conditions, the bedrock stays sealed. Choosing the right ground isn't just about stability. It's about picking a place that nature itself will help protect into the future. The rock becomes part of the containment system, a silent partner in the long-term defense against time. Once that location is chosen, the next step is turning solid rock into a functioning storage system, where it can operate safely without ever being opened again. At Finland's Onkalo site, construction starts with a main access tunnel that spirals more than 400 meters underground. From that central path, side tunnels branch off, like the veins of a leaf. Each one will hold dozens of copper canisters, spaced at precise intervals that manage heat and pressure. The design looks simple on paper, but every dimension, from tunnel width to the angle of a borehole, comes from years of thermal modeling and geological testing. When a canister is ready for storage, it's handled entirely by robotic systems. Radiation levels around spent nuclear fuel are far too high for human workers, so machines lower the capsules into position using automated cranes and guided rails. Cameras and sensors verify alignment to the centimeter. Once a canister is in place, engineers fill the surrounding cavity with the compacted bentonite clay, forming a tight seal. That clay isn't poured like cement, it's carefully layered and compressed to achieve the exact density needed for long-term swelling and stability. The tunnels themselves are reinforced, but not in the way you might imagine. They aren't lined with thick concrete walls or metal beams. Instead, the rock's natural structure does most of the work. The walls are treated to prevent loose particles, and then fitted with drainage and monitoring equipment. Over time, once all the canisters are eventually in place, these sensors record temperature, pressure, and humidity, data that helps confirm the system's stability before it's finally sealed. Thermal design is one of the most delicate parts. Spent fuel generates residual heat for decades, so the canisters can't be placed too close together. If they are, the heat would dry out or crack the bentonite buffer. Engineers use thermal diffusion models to calculate exact spacing, allowing the rock to slowly absorb and release heat without damage. Eventually, when the last tunnel is filled, the access routes will be closed, using a series of clay concrete plugs. At that point, the repository becomes passively safe, meaning it doesn't need power, sensors, or any human oversight to remain stable. It simply exists, relying on the natural properties of its materials and the geology around it to do their work for thousands of years. In a way, the repository becomes part of the Earth itself, a carefully designed extension of the landscape, built to last longer than any structure humans have ever made before. At first glance, the engineering of a nuclear waste repository seems purely mechanical. Metal, clay, and rock working together. But beneath that structure lies deep chemistry that determines whether this system will hold for 100,000 years or fail within centuries. Each material underground interacts with water, minerals, and even microscopic life. Understanding and controlling these reactions is the hardest part of long-term nuclear storage. That copper canister is the first line of defense. Copper was chosen because it corrodes slowly in oxygen-poor environments. Deep underground, where groundwater has been sealed off from the atmosphere, oxygen levels are super low. This keeps copper in a stable metallic state. If a little oxygen is present, a thin layer of copper oxide forms on this copper shell, acting like armor. It prevents deep corrosion from spreading. Researchers still test how different groundwater chemistries might change this balance, since tiny variations in chloride, sulfur, or carbonate can speed up corrosion. The next layer, the clay, swells when it comes into contact with water. Chemically, it's made of layered silicate sheets that trap ions between them. This property, called cation exchange, lets the clay capture radioactive particles that might escape if the canister ever cracked. The clay also buffers pH and slows the movement of any contaminants, turning the area into a nearly closed chemical system. Although it's not ideal, there's bound to be some groundwater when you try to set up a storage site, so the groundwater itself has to become part of the design. Scientists analyze its ionic composition, temperature, and acidity. Over time, these features might cause the bentonite to transform slightly, making new materials. But these changes are modeled carefully to ensure the clay still maintains its swelling and sealing abilities. Another factor is its oxidation-reduction balance, or redox chemistry. As water interacts with rock and metal, it can shift between oxidizing and reducing conditions. If oxidation levels increase too much, corrosion could accelerate. Repository design minimizes this risk by keeping oxygen exposure low from the start and using materials and minerals that help absorb or neutralize any reactive oxygen species that form later. Scientists also study how microbes might alter the chemistry. Even in deep rock, microorganisms can survive by consuming trace minerals or gases. Some bacteria produce sulfides, which can corrode metals. Experiments are underway to simulate these microbial ecosystems, testing whether they could meaningfully affect copper over thousands of years. So far, results suggest that with limited nutrients and sealed conditions, microbial activity will remain minimal. Each of these interactions between metal, clay, water, and rock unfolds on a timescale that's difficult to grasp. Chemical reactions that seem slow to us can, over centuries, shift the composition of minerals or create new pathways for fluid movement. To account for that, scientists run accelerated aging tests, exposing minerals to high temperatures or concentrated solutions to predict what might happen after thousands of years. The chemistry of stability isn't at all about preventing change. That would be impossible. It's about designing a system where every reaction moves toward balance instead of failure. Copper oxidizes slowly, bentonite swells and seals, groundwater chemistry stabilizes, and all of these things work together to create a changing, yet statically safe system. Even if the copper, clay, and bedrock perform perfectly, there's another problem that stretches beyond physics or chemistry. How do you warn people in the far future? Imagine someone stumbling across Oncolo 10,000 years from now. Civilizations could rise and fall, languages could disappear, and cultural symbols might mean something entirely different from now. How can we make sure that no one accidentally disturbs the waste, or mistakes it for a shelter, mine, or treasure? Scientists and designers have to think far outside modern human experiments. Simple warning signs or labels won't work. A plaque written in English or Finnish could be indecipherable. Pictograms might be misread, and even symbols we consider intuitive today, skulls or red paint, might convey the wrong message to people with entirely different cultural frameworks. To tackle this, researchers propose multiple strategies layered across time. Physical barriers, like large stone formations or ominous landscaping, create a sense of danger, even without understanding the details. Monumental structures, deliberately unsettling in shape or scale, might trigger instinctive caution. Some designs incorporate information archives, sealed chambers with multiple formats, text, images, and 3D models, to preserve the scientific knowledge needed to understand the site. Others suggest using a universal danger language, derived from semiotics, anthropology, and human cognition, to communicate risk as clearly as possible. Even so, there's no guarantee. People in the distant future might interpret messages in unpredictable ways, or may simply ignore them if their needs outweigh perceived danger. This is why the principle of passive safety remains critical. A repository must protect itself without relying on human behavior or technology. Communication is a supplement, not a solution. A way to reduce risk, not eliminate it. Deep under the Finnish forest, copper canisters sit inside tunnels, surrounded by clay and granite. They're designed to remain undisturbed for tens of thousands of years. Oncolo and projects like it show that engineering isn't just about solving immediate problems. It's about planning for a scale of time far beyond our own lives. Every layer of metal, clay, and rock represents careful testing, modeling, and scientific reasoning, built to last long after humans might even not be around. Designing for hundreds of millennia also raises difficult questions about communication. How do we warn people in the future? How do we anticipate environmental changes? Engineers and scientists address these problems through multiple layers of passive safety, redundancy, and attempts at long-term messaging. But there's no way to remove all uncertainty. At its core, storing nuclear waste is about trust. Trust in the materials we use, and the models we build, and in human planning. Success is not measured by immediate results, but by the ability of the repository to remain safe for future generations without human intervention. Oncolo stands as an example of what careful engineering and science can achieve when long-term safety is the goal. It is a system designed to work with nature, relying on stable geology, resistant materials, and redundant barriers. The copper canisters may never be opened again, but they serve as both a practical solution and a reminder. Responsible engineering sometimes means thinking far beyond our own time, and leaving something behind that will protect others long after we are gone.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.